I know it's been a long time, but I'm back and we're going to be doing a really cool video. So I've made a new friend. He's a professional at scraping and we're going to try and make scraping fun to watch. So we're going to be doing the mill table exclusively in this video. We're going to be scraping the top surface all the way through to the dovetails. So the goal of this video, and really the subsequent series that's going to follow, is to take everyone through the process of reconditioning one of these Chinese mills to have proper precision, have good scraped bearing surfaces on all the dovetails. And through the help of my friend Marcus, my new friend Marcus in the Gold Coast, who is he's an expert on the subject. I've learned so much from him. We'll be getting actual professional help as we go through this whole process. So we're really excited for it, and I hope you like it too. Scraping is one of those engineering skills that tends to be just as much of a practical discipline as it is an art. I think that's probably because machine builders tend to avoid it because it's slow and expensive and you need a very highly trained person to do it. But there is some serious advantages to it. And the goal of scraping is usually just to make a flat surface, but that's not always the case. A flat surface might be good for making like bearing surfaces that need to run straight and true. But it could also just be for mating two rigid mounting points, like mounting the column to the base of the mill. That's not a moving surface, so it doesn't necessarily need to be flat. They just need to mate up with a lot of contact points for rigidity and to hold the column square. So scraping is more about matching surfaces rather than making flat surfaces. To scrape those blue high spots, you'll usually use a scraper, which is creatively named. It's pretty simple, really. It's just a piece of steel with a handle, and you get this carbide blade. It's just a flat piece that's clamped in with this mechanism, a screw, and this would have probably a 135 millimeter radius across here. It's double-sided, so you can flip it over and use that one too. And those would be ground at probably a 5-degree rake right now. To sharpen the carbide, Marcus uses this low RPM disc sharpener called an AccuFinish with diamond discs on it. So that's a pretty typical looking one. However, Marcus really likes this pommel type of thing, or mushroom, I think he calls it, which is good for being able to sort of go off the palm and especially for going off the shoulder. This took me a while to get used to, but it actually is really valuable to be able to go off the shoulder when you're roughing, or really most of the time. It's quite good. So that's what he likes to use, and now I like to use that too. And once you've scraped off all of those blue high spots from the first print, you go and do another one, see if the print pattern has changed or if you just need to take more off of the same spot, which is common for the start at least. So why would we actually bother with scraping as opposed to surface grinding? Because surface grinding is faster, it creates exceptionally flat surfaces. What are the advantages to scraping? Well, remember, scraping isn't just about making flat surfaces. It's often about matching surfaces. So there's one benefit already. What if you just need to make one part fit well with another? Or what if it's very hard to grind those pieces flat? What if it's a big heavy machine that's hard or even impossible to set up in another machine for milling and grinding? Instead, you can just scrape that part in place. Scraping is also especially good for machine slideways because it doesn't produce a smooth surface like grinding. The slight valleys leave space for oil cavities, preventing it from being squeezed out and binding those surfaces together. To help visualize and explain the concepts in this video, we'll be using this digital replication of my mill table. Using this, I can easily produce certain effects like twist in the surface. I can bend it longitudinally and latitudinally. And I can also apply a height map over the surface to clearly show the effects of that twist and bend. And I can even produce concentrated high and low spots. Here's a key to help you read the colors. Think of the middle green as the idealized neutral height, the target of this visualization. This is what a perfectly flat surface looks like in this visualization. As the color in a certain area goes from green to yellow to red, it's deviating further from what we'll call acceptably flat. Now I'll introduce a pattern to imitate the texture of a scraped surface. The hope is that this will help clarify further what a surface is doing when it's scraped. I can also translate this directly to imitate a print against a flat surface plate. Throughout the rest of this video, I'll be using any combination of these effects to help explain what I'm talking about. So in this video, we're going to be focusing on the table of my mill. And that top surface of the table was ground from the factory in China. It wasn't very flat, as we found out. And when we printed it, before we ever touched it with a scraper, I don't have footage of it, but it looked something like this when it printed up. So as you can see, there's this weird sort of high patch in the middle. Otherwise, it was sort of like a concave, a spoon shape all over. But yeah, there was this weird high patch in the center, which we can only assume came from some issue with the surface grinder that they used. The top surface is ground at the factory, which causes it to heat up, which makes it bow upwards, but they keep grinding until it neutralizes and becomes flat, and when it cools down, it becomes a concave. Grinding also needs to hold the part rigidly in place, usually with a magnetic chuck. This will warp the part some amount, which springs back once released, whereas scraping doesn't produce any significant force on the part. One of the first things you want to do when scraping a flat surface is remove convexity, because if it's rolling around the center area, it'll print up a large area that isn't actually the high point. In theory, you could actually print up a whole convex surface by just rolling it all the way around, and it's misleading. You'll look at it and think it's flat, because look, it's all blue, I've got a flat surface, but it's a misleading print, so you need to stabilize the surface. A way to check for convexity is to lay the table on the surface plate, put an indicator on one corner, and press down on opposing corners to see if you can rock it back and forth. So as an example of a pivot test, this surface should be pretty flat on the table. So it should have a fairly vague sort of pivoting action. I can tell that it's pivoting around here a little bit, so maybe that's still a slight high spot, but it's kind of vague and it's hard to move. If there was a convex and it was sitting at this point very distinctly, it'd be easy to spin and it would clearly pivot from there. If it was twisted and this was the high point, it would very clearly pivot from that point over there. And if I was moving this side, it would pivot from there. First, we roughed out that patch near the middle. Then we took out more material from the middle to eliminate any further convexity. Then gradually brought in the corners and ended up with a stabilized surface. And once the roughing was done, we started focusing on getting a higher PPI. I found it really easy to start scraping lighter and lighter because you don't really know how much material you've removed yet. When you're not used to it, it's hard. You're worried that you're going to stuff up the surface. So you start scraping lighter and lighter, and you might even start being a perfectionist and try and get all these little bits just right, when really you've got heaps more material to remove before you're even close to having a flat surface. So when you start doing that perfectionist, light little scraping action, Marcus calls that bitching. He tells me that Richard King calls that chicken scratching. So this is what chicken scratching looks like. I suppose this chicken scratching, bitching it thing is a consequence of not really having a feeling for how much material you need to remove or how much is left to go. You want to be perfectionist and not stuff it up. But the fact is, you've got plenty of material left when you're roughing. Really, you need to do roughing before you start finishing. It's easy to start getting perfectionist. As long as you are staying consistent across the whole surface, so you're not going back over the same part that you've scraped and you're just keeping an even pressure, and even the sharpness of your edge can start to affect your depth. So you need to keep things consistent across the whole surface, each pass, and then you should be fine. Right now would be a good time to talk about these magical things. These are precision ground stones. So they've had these surfaces ground to a very flat surface. And what you do is you rub them together until you get all the grit out. And then you use that to grind away or stone away the peaks from your scraping and also the burrs. And it takes a lot of expertise out of scraping, so you can get nice flat plateaus for good contact, and it polishes them very nicely too. So these are super nice. After roughing, we moved on to finishing, and I really like the look of pull scraping, so I was able to stick with the mushroom handle and also keep the large radius on the carbide, and you just shift the angle that you hold it at. So instead of sort of a forward action, you shift it up really vertical and you pull. It's in the name. And I basically spent as much time as I dared to try and get as many contact points out as I could. It's not a super high contact points per inch, but for the surface, Marcus tells me it should be good enough. The other option is more scraping, which is like a curl action, and we did do that for most of the other surfaces on the table, but I wanted something a bit different and nicer for the very visible top surface of the table. Next, we focused on getting the flatways actually flat and parallel to the tabletop that we just scraped. Surprisingly, but also logically, you only really need to make the flatways parallel this way, relative to the top surface. The two flatways don't need to be parallel in the perpendicular direction, and they don't even need to be coplanar. This is because you're just going to be matching the saddle up to whatever results you get on these flatways. Also, quite importantly, chances are your flatways won't be coplanar. And that's okay, because from the factory they would have matched the saddle up and made everything aligned. So if you mess with that too much, you'll be giving yourself more work. Just focus on making the flatways flat, not messing with their geometry. If the flatways are not made parallel to the top surface, as mentioned, then this is the consequence. As it slides along the x-axis, the top surface relative Z location changes. We laid out the table with the top facing down, and with a 10,000ths indicator on a sled, we swept across the surface to measure the variation. They weren't awful, but definitely could be improved. Even if they were geometrically good, they have a terrible surface finish from the factory that scraping can fix. Doing these flatways was where I really started to learn about the process of step scraping, which is where you use an indicator to run along the surface, and you want to mark out a topographical map of the height variations and the intervals between each graduation that I used was in 5/10,000ths of an inch, because our indicator was reading 10,000ths, and the depth of a single scrape that Marcus was reading on his work was about 5/10,000ths, so it seems like a good sort of graduation to work off of. But you should always check the depth of your scrape before you decide on the graduation size. It can be a little tricky to get the whole surface mapped out perfectly, so don't try and do it perfectly. Once you've done your topographical map, you're ready to start scraping. Except you're not ready, because you need to actually relieve the area where that gib sort of occupies, because there's not going to be any contact there, and it's hard to scrape into that inner corner where the flatway meets with the dovetail. So you just sort of go nuts in that area. It's usually only a small section where the gib would live. There's no contact with the saddle or the base. So you just rough it out. We even used a warding file to sort of file all that out. If you want to be a complete nutcase, you can even get an angle grinder and just grind away that whole inner corner and just relieve it. Then you can come back and work on your topographical map. So this is how the step scraping works. We've got what would be a bulge here, and it comes down to basically our 0 point. We want to get everything level with this low region. So you'd start off by scraping the high point. Then on your next pass, scrape in the perpendicular direction to avoid chatter. And you'd do that, and also go over the previous region. And then the next one, switch directions of scraping to avoid chatter, and go over all of the previous ones. And at this point we'd stop because the intention is for all of this to now be roughly level with the low point. And we don't want to scrape this because that's our target height. Once your topography is within about 1/1000th of an inch of parallelism, you can use a straight edge to start printing and scraping as usual. This time we used more scraping to finish. This is a nice shot of the more scraping that we've done on the back face. They're fairly irregular because we were just targeting the high spots. But these two, especially this one, is a pretty good example. You want it to be sort of symmetrical along this center line. And you can see how it starts off very lightly and gradually leads in. This is where the high spot would have been, so that's the target point. It's a very concentrated scrape, and then gradually leads back out and doesn't leave a burr. Whereas something like a pull scrape or other type of scrapes might scrape forward and then stop and lift up, leaving a burr at the point where it stopped. But this one just gradually leads in and out. Scraping in the flatways was very much the same story as the top surface. It was high on the sides, and then you gradually bring those in through roughing. And eventually, once you get to a nice flat, roughed surface, you start chasing higher PPI. Next up was the back face of the mill. Next up for scraping was the back face, the face along the back side of the table. We didn't worry too much about aligning that or squaring it up. We just went straight into scraping it into a flat, and that'll be good enough for our purposes. And those purposes are to use it as a straight edge reference against the dovetails for when we're actually trying to align the dovetails, because those are a very important part, obviously. It's also just a really nice luxury to have such a trustworthy edge that you can square things up against when you're working on the machine. Like you could put an engineer's square against it and get something that's, you know, is going to be quite square to the travel of the x-axis. And it also looks good too, if anyone's ever looking at the back side of the mill table. So we went straight into breaking up the surface with a single roughing pass over the whole thing. Then print the face up and make sure it's not convex. You always want to look for convexity or twist when starting. To make sure there's no convexity going on, we scraped a line down the middle longitudinally and made sure that there was no contact transversely. Now you basically just repeat the same usual process of scraping, printing, scraping until you're ready to start roughing. Finishing. Now, I was pretty anxious about messing with the dovetails. If I didn't have Marcus's help, I definitely wouldn't have messed with them. I wouldn't have known how to, and I wouldn't have had the tools to do it either. But with his help, it was actually pretty easy and satisfying too, and quick too. The goal is to make them flat and make them parallel to the table only in the longitudinal direction. The angle of the dovetail wasn't messed with because I guess it just didn't really need to be. How do we actually measure the parallelism in that critical axis when the dovetail face is, tilted so dramatically? Well, that's what we scraped the back face for. That's the reference straight edge. So we made up this sled out of a big piece of scrap cast iron, and it fits over the edge of the table, and then you can use the back face and then either the flat way that has already been also scraped flat, or the top surface of the table, which has also been scraped flat. Once you've got that pressed up against those two surfaces, you've got one final degree of freedom, which will run a very straight line. So you attach a mag base on top of that, put it on the dovetail surface, and now you can measure pretty well the parallelism along the dovetail. Now to explain that a bit further, we started off with a 0 point around about here, and then it progressed to about 5/10 of a thousandth, then about 10, and then 15. And so you scrape more here and then more along there until you start to level it out. At this point, we've gotten up to still 0 here. By about here, we've got 5/10,000ths, and it remains 5/10,000ths across the rest of that length. So we've got it almost geometrically correct, and then you want to work on the surface. To scrape the dovetails, you do need a dovetail straight edge, but beyond that, it's very much the same step scraping process. The other dovetail is a bit of a different story because the front face of the table it's not a good surface to make a reference straight edge out of like we did with the back face. So to get around that, you put the mill down on the surface plate with that back scraped face, the reference edge, down on the table. And then you get Hoffman rollers, which are cylindrical rollers that are more round than dowel pins. And you want to put them inside the dovetail and run an indicator along the apex of those rollers. And you measure different points along the dovetail, and that gives you a reading of the variation because you're referencing against that back face on top of the surface plate. You could also use a micrometer that pinches over the two dovetails with rollers inside there to get a variation, but then you risk the chance of stacking up on the error because you're going from the back face to the dovetail and now measuring off of that dovetail to scrape the next dovetail. So it's better this way. And if you don't have Hoffman rollers or gauge pins and you're using like a dowel pin, you need to know that dowel pins can actually, they're not ground between centers, so they get a trilobe sort of shape. And so if you measure across that dowel pin with a micrometer, it'll always read the correct diameter because the opposing sides sort of cancel out to produce the same outside measurement. But as soon as you put it into a V-block or a dovetail like this, that sort of camming action becomes a problem. You can get around that still if you rotate the dowel pin in the dovetail so that you can get a reading of the variation, the minimum and maximum variation, and then you can account for that as you take your measurements all the way along the dovetail. But obviously it's a lot more work to do it that way and prone to error. So if you can, get a gauge pin or Hoffman rollers. Except for that different approach to measuring the second dovetail, the rest is the same as the first. You measure, mark out the topography, and finish scrape.
Hey, as you may have guessed, I'm Marcus and it's my shop that Christian's been filming in. I thought I'd just give a quick little disclaimer in that some of the scraping shown is not necessarily subpar, but it's not picture perfect. Some of the prints, far from ideal. I think he's done a great job of conveying a lot of the different techniques involved. Hopefully we can do some more in future. If you have any suggestions, obviously put them in the comments. And if you're more interested in scraping and you want to learn more, there's a fantastic Facebook page for Australian scrapers, Oz Hand Scraping Machinery Building. So if you've got any questions that you want answered in detail, feel free to join the page and have a little query.
And that makes a fully scraped mill table. It was a lot of work. It was about 10 months making this video, lots of on and off and other life commitments. But it's been really cool to learn. Next time we'll cover a lot of different topics as well, and we'll be doing things like applying Turkite, which is a variation of Teflon. This was the second in a series of building this CNC mill, and it's the first in the sort of sub-series about scraping it in. And these videos will be separated by sort of the castings that make up the machine. So the next one will be about the saddle,
And it'll be just in useful chunks, and they're always followed up with an article. So in the description, there'll be an article on my website where you can read extra detail, and there'll be a section from Marcus as well, which is, it'll be more specific and in more detail. So thank you for watching. I hope you had fun. Stick around for next time, and give it a like if you liked it.
I hate to be the one to tell you this, but if you've made it this far without skipping, there is a very good chance that you have autism. The good news is autism very well applies to scraping, and you'll do very well in scraping as a hobby. So there are a few concepts in this video. One of them I know I'll get some comments on, scraping that back rail face. No real professional rebuilders would do something like that. I mean, most professionals would just get the table ground. It's not necessarily the most efficient way, but it is an excellent way. And some of these concepts can be a little bit left of field, but I think having them up your sleeve is something great. Maybe just cut it off at great.